Howdy. We're going to be talking this evening about the second derivative of f and its meaning for the graph of f and also for f prime. I want to start by reminding you of some things that you already know. You remember that we said before, if f prime is greater than 0 on an interval a to b, this means that f of x is increasing on a to b. Likewise, if f prime is less than 0 on a to b, then f is decreasing on a to b. So, for example, we have the function f of x is equal to x cubed minus 3x. And we have then f prime is equal to 3x squared minus 3. If we set f prime equal to 0 and solve by factoring, you can see that we get two critical points, x equals 1 and x equals negative 1. And if we construct for ourselves a well-labeled number line with our two critical points on it, negative 1 and 1, and we test the sign of f prime in each of the corresponding intervals, we might pick a number such as maybe negative 2 for this interval. And if we do and plug it in, then we see that f prime is a positive value, in fact, positive 6. If we try x equals 0 for this interval, and we plug in, we see that f prime is a negative on this interval. And if we choose a number larger than 1, such as 2, and plug in, we see that we get a positive value for f prime on this interval. And so that would allow us to say that f is increasing on negative infinity to negative 1, together with 1 to infinity, because f prime is greater than 0. And here is our justifying language. And we remember that the mere expression of a number line is not enough. We have to have the justifying language because f prime is greater than 0. Likewise, we can say that f is decreasing on the interval negative 1 to 1 because f prime is less than 0. Now what I'd like to do is to consider the meaning of f double prime. Everything that we've done so far has been familiar to you. But now let's take a look at f double prime using the same function. Of course, to get f double prime, we first have to find f prime, and there it is. And now we have f double prime is equal to 6x. You can see that f double prime in this particular case is less than 0 when x is less than 0, and f double prime is greater than 0 when x is greater than 0. What does this mean? To understand this, I want to take a look at the graph of f prime. F prime is equal to 3x squared minus 3. Clearly that's going to be a parabola with an intercept down here at 0, negative 3. And we already know from the previous page that it has two zeros at x equals negative 1 and x equals 1. To understand the meaning of f double prime, we want to always remember this. F double prime is the first derivative of f prime. F double prime is the first derivative of f prime. And this is so important that we're going to give it stars. F double prime is the first derivative of f prime. So if you look over here at the graph of f prime, you can see that f prime itself is positive here and negative here, just as we showed on our number line, our f prime number line on the previous page. But if we look at the slope of f prime, which gives us the derivative of f prime, in other words, f double prime, then you can see that f prime's slope is negative when x is less than 0, and it is positive when x is greater than 0. In other words, f double prime is negative when x is less than 0, and f double prime is positive when x is greater than 0. The first meaning of f double prime then, because it is the first derivative of f prime, it is the slope of f prime. When f double prime is positive, then f prime will be increasing. When f double prime is negative, then f prime will be decreasing, because f double prime is the first derivative of f prime. You say, okay, that's fine. But what influence does that have on the graph of f? So now I want to consider what the graph of f looks like. And here is our f once again. F of x equals x cubed minus 3x. If we go back for just a minute to the previous slide here, we found that f is increasing up to negative 1, then decreasing to 1, and then increasing again after 1. And we have enough experience with cubic functions like f of x to know that this means that f is going to be increasing and decreasing and increasing again. In fact, I can actually find the zeros simply by setting f of x equal to 0 and factoring. And I find 3 zeros, one at x equals 0, one at x equals positive root 3, and one at x equals negative root 3. Now here's what I want you to observe about the graph of f. You can see that from x equals 0 and all the way out here, the graph of f is curved upwards. It's like a bowl that catches rain. And it is curved upwards because its slope is getting steeper and steeper as x gets larger. We call this state of affairs concave up. We say that f of x is concave up for x greater than 0. And the reason for that is that its slope is increasing. Its slope, which is f prime, but we already know that if f prime is increasing, then f double prime is positive. In other words, for all of the region from x equals 0 and beyond, f of x is concave up for x greater than 0 because f double prime is greater than 0. What it means to have a positive second derivative is that your curve will be shaped concave up, because that positive second derivative forces your slopes to increase. Likewise, for x is less than 0, you can see that the curve is shaped concave down. It is curved downwards. For x less than 0. Why? Because if I draw tangent lines, you can see that the slope is decreasing. And again, the slope of f is f prime. And the reason that the slope is decreasing, as we said previously, is that f double prime is less than 0. In other words, a negative second derivative forces the slopes to decrease, which then bends the curve downwards. In other words, f double prime is the quantity that bends the curve either upwards or downwards. Positive second derivative is going to force the curve to be concave up, and a negative second derivative is going to force the curve to be concave down. Let's summarize all that information right here. If f double prime is positive, that's going to force f prime to be increasing, which in turn is going to force f to be concave up. If f double prime is negative, that causes f prime to decrease. I should spell increasing with an ing, shouldn't I? And that's going to force f to be concave down. This is the second big deal of our lecture, so it gets stars also. Okay. Now, right where the curve changes from concave up to concave down, right at this point, or you might say concave down to concave up, if we're going increasing x, which we usually do. So right at this point right here, we have a change in concavity. Our curve goes from concave down to concave up. We're going to call any change in concavity a point of inflection on the graph of f. A point of inflection. And this is going to be any point where the graph of f changes its concavity. From concave down to concave up, or vice versa, from concave up to concave down. If the graph of f is changing its concavity, and the concavity is controlled by the sign of f double prime, then this necessarily means that at this point, f double prime will change signs. So we're going to think of a point of inflection as a place where f double prime changes signs. Well, let's do this. Let's take a look at a couple of graphs. I want to consider a graph of f and then a graph of f prime, and see if we can read information about f double prime off of it. So here is our first graph. It's going to be a graph of f of x. And let's make our graph of f of x look something like this. I like that. And now our task is going to be to create well-labeled number lines for f prime, which we already know how to do, and for f double prime, which we are learning right now. Since this is a graph of f, its slope will be f prime. And so we can take a look at the places where the slope of f is 0, here, here, and here. And those three places give us the zeros of f prime, just like that. And where f is increasing, f prime will be positive. Where f is decreasing, f prime will be negative. And right over here, f starts to decrease again. And so there's our number line for f prime. And we're pretty comfortable with that process. You guys are pretty good at it. Well, what about f double prime? F double prime is going to be positive anywhere where the graph of f is concave up. You can see pretty easily that f is concave up in this region right here. And you can also see that f is concave down over here, and also over here. It curves downwards in both of those places. Well, what about the points of inflection? The points of inflection are going to be the places where f double prime changes signs, and that's going to be somewhere right around in here. And to find the spot in the best possible way, we're going to look for the place where the graph becomes really the flattest, almost like a straight line. Because at that point, f double prime will be equal to 0. And of course, f double prime cannot change signs without either going through 0 or becoming discontinuous. So right here where the curve is the flattest is my best estimate for the place where f double prime changes signs. And that's right here at x equals -3. And then again, right about here, where f becomes the flattest again, this place is a good candidate for f double prime to be 0. So the points of inflection of f will be at places where the graph is the flattest, most like a straight line. To use a math term, most linear. Now sometimes students will have trouble visualizing concavity. Concave up and concave down. It was pretty easy here, but in case it was difficult for you, I want to show you something else that's kind of neat. If you take a look at the graph of f for x's that are less than -3, you can see that the tangent lines to f here all sit on top of the curve, or another way of putting it is the curve lies below its tangent lines. And that's not an accident. Get these out of the way. There we go. If f is concave down, it lies below its tangents. And this must happen every time. Why? Because if f is concave down, f prime is necessarily decreasing, which means that the graph of f will increase not quite as fast as a straight line. Straight line has a constant slope. The graph of f here has a decreasing slope because it is concave down. So a straight line will beat it. It will lie on top. It will go above it. And the result is that f will lie below its tangents. Likewise, if f is concave up, it lies above its tangents. And the reasoning is similar. If f is concave up, then f prime is increasing, which means that the curve will grow faster than a straight line, which has a constant slope. F with an increasing slope is going to grow faster than a straight line with a constant slope. And so f will go above its tangents. And then finally, right here at the point of inflection, if I take a look at the tangent line, look at what it does here at x equals -3. We'll draw the tangent line in purple. Right here at the point of inflection, take a look at what that tangent line does. It goes right through the curve. It lies above the curve to the left, and it lies below the curve to the right. And because the curve is so linear right there, it's kind of hard to see. The tangent line looks like it melds with the curve pretty much. But you can see it's definitely above to the left and below to the right. The same thing happens with the point of inflection over here at x equals 6-ish. The tangent line is below to the left and above to the right. The tangent line goes through the curve. So at a point of inflection, the tangent line goes through the curve. This is a lot of information. So I want to take a moment to just summarize everything that we've said so far, and then apply that to a graph of f prime. Our story so far. If f prime is positive, then what do we know? We know that f prime is increasing because f double prime is the first derivative of f prime. And we know therefore that f is concave up, which means that it is above its tangents. Likewise, if f double prime is negative, then f prime is decreasing, and f is concave down. Or in other words, it lies below its tangents. And this really summarizes the important information here. In addition, we have points of inflection. These are the places where f double prime changes sign. And the places where the tangent line goes through the curve. Where the tangent line goes through the curve. Okay, with all of that in hand, let's now consider a graph of f prime. Here's our second graph. And let's let f prime look like this. Somehow, some way, we came across a function whose derivative was given to us in this graphical form. Reading this graph of f prime requires us to be careful about interpretation. If I want to create a number line for f prime, I will now be interested where f prime is negative, and where it is positive, and where it is 0. If I wish to create a number line for f double prime, then I'm going to remember that f double prime is the first derivative of f prime. In other words, it is the slope of f prime. And so when f prime is increasing, then f double prime will be positive. When f prime is decreasing, f double prime will be negative. And when f prime is increasing again, f double prime will be positive. And right at the places where f prime has local extrema, those are the places where f double prime will change signs. So here is our f double prime number line. How could we then use that to interpret the shape of f? We would say that f of x is concave up on what intervals? Well, on the interval -10 all the way up to -2.5, because f double prime is positive. We would also include the interval from 4 out to 10. If you wanted, if in your mind you were thinking that the graph of f extends out to infinity, then I would be okay with that. But I was limiting ourselves to -10 to 10 because that's all that we can see. We would say that f of x is concave down on the interval -2.5 to 4 because f double prime is less than 0. And so to get the concavity of f, we simply looked at the sign of f double prime. Finally, we would say that f of x has points of inflection. POI is a universal abbreviation for points of inflection at x equals -2.5 and x equals 4. Why? Because f double prime changes signs. And every year I have some poor schmo that wants to tell me because f double prime is equal to 0, and this is wrong. Points of inflection are not places where f double prime equals 0, but places where f double prime changes signs. Well, that's how you read graphs. What I'd like to do now is to consider how this works with a function given in terms of an equation. So let's consider f of x equals 4x cubed minus 12x squared. No, actually, excuse me, f of x equals x to the 4th minus 4x cubed plus 16x. This is the function that we wish to consider. And our task is going to be to find the points of inflection of f and the intervals for which f of x is concave up. And because we're looking for points of inflection and concavity, we know that that information will be found in f double prime. And so we immediately compute first f prime, which is 4x cubed minus 12x squared plus 16. And then we compute f double prime, which is going to be 12x squared minus 24x. And because we are looking for points of inflection, places where f double prime changes sign, we are going to do that by finding the places where f double prime is equal to 0 and creating an f double prime number line. When we set f double prime equal to 0, we remember that factoring is our friend, and we factor immediately to get two solutions, x equals 0 and x equals 2. And now we consider values of x that are first less than 0, perhaps -1. And when I plug in x equals -1 into f double prime, I get a positive value, specifically positive 36. I consider a value between 0 and 2, perhaps 1. When I do, I get -12. Just negative, that's all we need. And then when I plug in a value of x that is greater than 2, perhaps 3, then I get positive 36. So this is my f double prime number line. Based on this, I can see that f double prime changes signs at x equals 0 and x equals 2, which means that f has points of inflection at x equals 0 and x equals 2. And the justifying language is right here. Okay, well, I get a twofer, because having identified the points of inflection, I can now immediately see from that number line that f is going to be concave up. Where? Right, exactly. Negative infinity to 0 together with 2 to infinity, because, justifying language, f double prime is greater than 0. That's it. Pretty simple. Okay. We're about to take all of this and do some curve sketching. If you would like to take a break at this point and pause the video, this might be a good time to do that. When you come back, we're going to use f prime and f double prime to get the shape of two different curves. Welcome back. Our task is going to be to sketch the curve f of x equals 2 minus x cubed. And we're going to do this by considering all of the information that we can get from the equation of f, from the equation of f prime, and then from the equation of f double prime. What can we get from f? Well, what we can get from f are, first of all, any domain restrictions that we might happen to have. In this particular case, f of x is a polynomial, which means that its domain is all real numbers. We also consider any possible zeros. I look to factor f of x, and I don't see anything obvious that jumps out at me as a factor. I don't see any common factors, for example. But I do a quick check that I often do, and that is I check x equals 1 and x equals -1 in case they give me any easy to find factors. And sure enough, when I plug in x equals 1, I get 2 minus 1 minus 1 is equal to 0, and that immediately means that x minus 1 is a factor of f of x. So I have a 0 for my f, which is x equals 1, and I can possibly find other zeros by factoring out the x equals 1, which I'm going to do with synthetic substitution. Remember that with synthetic substitution, you line up your coefficients in order here. So this is the coefficient of x cubed. This is the coefficient of x. Right? And this is the coefficient of 2. So I reordered this in terms in order of highest power. And then you bring down, multiply. 1 times negative 1 is negative 1. Add, multiply, add, multiply, and add. And we get a 0 here, which is not surprising because we knew already that x equals 1 was a 0. And these coefficients here are now the coefficients of my reduced polynomial. So that f of x is equal to x minus 1 times negative x squared minus x minus 2. Well, I see a negative 1 factor that can come out of that. And then I look at this guy and realize that it is definitely not going to factor. And when I try its discriminant, 1 squared minus 4 times 2 times 1, which is less than 0, I realize it has no other real zeros. It has just this 1 0, x equals 1. So the information that we get from f are domain and then zeros by factoring if we can. For f prime, matters are much simpler. First of all, we compute f prime of x, and f prime of x is equal to negative 1 minus 3x squared. And we set that equal to 0 so that we can find critical points and local extrema. And when we set that equal to 0, we discover this requires x squared to be negative 1/3, which has no solution. So there are no critical points for f prime, and f prime is either going to be positive or negative on the entire real line. Let's construct a number line here, making sure that we label it with our f prime, and plug in a value for x, any value for x. I like x equals 0, and when I plug in x equals 0, I see that f prime is negative. What this means is that f is decreasing for all real numbers because f prime is negative. And now finally, we have the information that we can get from f double prime. And f double prime is the derivative of f prime for negative 6x. And I'm going to set that equal to 0 as well to find the critical points. And I get 1, x equals 0 as a critical point. And when I create for myself an f double prime number line, please notice that it is labeled as f double prime. And I plug in a value, let's say x equals negative 1, I get positive for my second derivative. I plug in x equals 1, I get negative for my second derivative. So that f is concave up on negative infinity to 0, because f double prime is greater than 0. And f is concave down on 0 to infinity, because f double prime is less than 0. And this is enough information to get a really good sketch of our graph of f. We'll go back to the top here. We have no domain restrictions. We have a single 0 at x equals 1. So our graph of f is going to show 1, 0 at x equals 1. It is going to be decreasing on its entire domain. So its general shape is going to be in this direction, going through x equals 1. And it is going to be concave up or curved upwards until x equals 0. So I can sketch f so that it is curved upwards or concave up until x equals 0, and then concave down thereafter. I don't want to make it too flat here. Let's improve our graph just a little bit. There. So our graph here has a point of inflection at x equals 0, where the graph is most like a straight line, but it is not horizontal because f prime is not 0 at that point. So the graph of f looks something like this. Now if you have a calculator, you can get it out and sketch it, and you'll see that this is a pretty good sketch indeed. So let's summarize what we did. We used f to find domain and zeros. We used f prime to find increasing and decreasing and local extrema. There were none in this case. And we used f double prime to find concavity and points of inflection. And that is enough to have a very respectable graph. Let's take a look at one final example, which is going to be a more advanced example. We're going to consider the function f of x equals x times the square root of 4 minus x. Or if I rewrite it, x times 4 minus x to the 1/2 power. And we're going to do the same process that we did for the other ones. We're going to start with f and consider domain restrictions. And you can see that because I cannot take the square root of a negative, therefore 4 minus x has to be non-negative, which means that x has to be less than or equal to 4. And I can also see that there are two obvious zeros. One is when x is equal to 0, and the other is when x is equal to 4. So already I can see that my graph of f is going to have two zeros. Just like that. Now I go about the business of finding f prime. And the reason this is a more advanced example is that f prime is a little bit more difficult than in the previous example. So we have first times the derivative of the second plus the second times the derivative of the first, which gives us x times 1/2 times 4 minus x to the minus 1/2 times the derivative of the inside plus 4 minus x to the 1/2 times 1. And now we're going to need to clean this up a little bit. This is going to give us x times 1/2, or x over 2, times -1, times 1 over the square root of 4 minus x for our first term, plus the square root of 4 minus x for the second. Take a minute to make sure that you agree with the algebra here. Now, because I want to set this equal to 0 and evaluate the sign and so on and so forth, it makes sense to get a common denominator here. So I'm going to multiply top and bottom of this term by 2 roots 4 minus x. And on the top here, I'm going to get 2 times, notice that the square root of 4 minus x times the square root of 4 minus x is simply 4 minus x. So that when I now add these with a common denominator, I get negative x plus 8 minus 2x all over 2 root 4 minus x. And this is our simplified derivative. Notice that the calculus part is not hard, but the algebra took us, well, 1, 2, 3, 4 different steps. So you have to be patient with the algebra, and you have to be careful with it. Now, to find critical points, we set our derivative equal to 0, and we also consider places where the derivative does not exist. When we set the derivative equal to 0, this means that the numerator must be 0, or x is equal to 8 over 3 is our critical point. Also, we observe that our derivative does not exist when x is equal to 4. What does this mean? Well, this means that I'm going to have, with regard to number line right here, I'm going to have a 0 for f prime at 8/3, and I'm going to mark the place where the derivative does not exist as a circle with an x. And if I plug in a value of x that is less than 8/3, let's say 0, and plug that into our f prime here, then I get a positive divided by a positive is positive. And if I plug in a value, let's say 3, that is greater than 8/3, then I get a negative value divided by a positive, so that my f prime looks like so. I notice that I have a local max at x equals 8/3, and that because f prime changes signs from plus to minus, and I am increasing on negative infinity to 8/3 because f prime is greater than 0, and I'm decreasing on 8/3 up to 4 because f prime is less than 0. Okay, good. So already I have a sense of what my graph is going to look like, going back up to my graph. If this is 8/3 right here, or 2 2/3, then my graph is going to go up, and then it's going to go down, just like that. The question is, will it be concave up or concave down? So that brings us to our second derivative. Remember that f prime was equal to 8 minus 3x over 2 roots 4 minus x. And so now f double prime is going to be low d high less high d low all over denominator squared. Now we're pretty happy with the calculus part, but now we have some algebra to deal with. So let's do that patiently. First we have all of this times negative 3 minus 8 minus 3x times constant multiple rule times 1/2 of 4 minus x to the minus 1/2 times the derivative of the inside. And all of this is now divided by 4 times 4 minus x. Let's clean up a little bit by gathering factors. Negative 6 root 4 minus x. We have a factor of 2.5 cancel. Negative 1 times a negative gives me a positive. And 4 minus x to the minus 1/2 is, again, 1 over root 4 minus x. Okay, so we're a little bit happier with this. We still need to continue to simplify because we have a compound fraction here. So we're going to clear the fractions by multiplying the top and the bottom of our fraction by root 4 minus x. And when we do, we distribute to each term, and we get negative 6 times 4 minus x plus 8 minus 3x. All of that over and now we can distribute here and get negative 24 plus 6x plus 8 minus 3x all over. And you know, as I look at the bottom there, it occurs to me that if I changed my mind and factored out the 4 again, and what I have is 4 minus x to the first power times 4 minus x to the 1/2 power, and when you add the exponents, you get 4 minus x to the 1/2 power, or 4 minus x to the 3/2 power. And in the numerator here, then I get negative 24 plus 8 is negative 16, plus 6x minus 3x is plus 3x. And there's my f double prime. Whew! That was some significant work to clean it up. What will it tell us? Well, we're interested in critical points. We're interested in places where the second derivative is either equal to 0 or does not exist. Something very interesting happens when I set the second derivative equal to 0. Of course, this means that the numerator must be 0, or x is equal to 16 over 3. Now, a naive student at this point would immediately draw his f double prime and put a 16 over 3. But if you're thinking a little bit more carefully here, you realize that 16 over 3 is 5 1/3. And 5 1/3 is actually outside of our domain because our domain is x's that are less than or equal to 4. So this critical point of 16/3 is actually a phantom critical point. And it simply happened because of the way that the algebra worked out. So in fact, our only critical point for f double prime is going to be the place where f double prime does not exist, and that's right at x equals 4. And when I test a value, any value, of x for x less than 4, let's try 0, then I get a negative over a positive. Or in other words, f double prime is negative on the entire domain of the function. What does this mean about our graph? This means that our graph is concave down for its entire domain. And the graph of f is therefore going to be curved downwards, just like this. And if you take a look on a graphing calculator, you'll see that this is in fact a very good sketch of f. Well, I hope this was helpful to you in terms of understanding the meaning of f double prime, also in terms of understanding how function sketching works. Let's summarize our function sketching process. We can use the equation of f to find domain restrictions and also to find any obvious zeros for f. If we were to have them, we would also use it to find vertical asymptotes and horizontal asymptotes. We then use f prime to find places where f is increasing and decreasing,